Hi everyone, welcome back. Today we're going to be working on the substitution rule. And the substitution rule here is given to us for integrals. It says that if u is equal to g of x, and if this is a differentiable function whose range is an interval I and f is continuous on I, then the integral of f of g of x multiplied by g prime of x dx is equal to the integral of f of u du. Now, this is going to be very important for us because this is going to allow us to evaluate different types of integrals that we might have previously not have been able to evaluate with just the power rule that we're accustomed to. So, using this technique for substitution, we're going to need to make sure that as we're identifying the integrand, we need to identify, number one, that we have a function composition, and number two, that the function composition is then multiplied by the derivative of the inside function. If those two cases are met, or if those two requirements are met, then we're going to be able to use the substitution rule. Now, to illustrate this, let's consider y is equal to sine of x squared. So if we're looking at y is equal to sine of x squared, and if I were to say, let's take the derivative for y. Well, we would know that taking the derivative for y, we would get y prime, take the derivative of the outside function, which would now be cosine of x squared, and then multiply by the differential on the inside function, so multiply by the derivative of the inside function, and we would then get that y prime is 2x multiplied by cosine of x squared. And so this is what we were doing when we started back in chapter 2, and we were taking these derivatives. So this was differentiation. Oops. Let's take a little more time there. There we go, more space. And now what we've been learning in chapter 4 is that we can take these antiderivatives, or as we're calling them, these integrals, and we can work with them just a little bit more. So what we want to do here is we want to work backwards. We want to say, looking at this derivative, what's its antiderivative? So in other words, we want to work backwards. I'm just going to say this is going to be an integral. So if we were looking at the integral for 2x multiplied by cosine of x squared dx, then we would be asking ourselves, what derivative did we need to take, or what function did we take the derivative for to get us 2x times cosine of x squared? Well, naturally we see on the screen that we had taken sine of x squared. But the process here is, how do we then go about it? Okay, so we definitely know the answer because, again, it's on screen here, that we would get sine of x squared. Be careful here because this is an indefinite integral, therefore we need a constant. But again, the question lies in, how do we go about it if we didn't initially know what the function was? Well, that's where the substitution rule comes in. Remember, I said that we needed two items or two components to look at. Number one, we need a function composition. So looking at my integrand of 2x times cosine of x squared, do we have a function composition? The answer there is yes. We do have a function composition. That function composition is taking cosine of x squared, and it's being composed with x squared. So naturally, what I want to do is I want to extract that. I want to say that u is going to be equal to x squared. And that's what this substitution rule is saying. Saying that if you have an innermost function, make that your substitution. Furthermore, we're then going to need to see, or we're going to need to check to see if the derivative of that substitution is multiplying my integrand. So we have to check the differential here. Check the differential, du is going to be 2x dx. And you're going to see here that we do see, and I'm going to say this was x squared, that we do see our differential 2x dx. That differential I will highlight here, 2x dx, and it is multiplying the function. That's my 2x dx. Therefore, what we could do then is we can rewrite this integral. Instead of saying that we have 2x cosine of x squared for our integrand with respect to dx, we're going to use the substitution here. The substitution says if you have the substitution that you're making, so we have cosine of, no longer it's x squared because that substitution is now u. So we're doing cosine of u, there we are, and then everything else left for that integrand, that 2x dx, that 2x dx matches directly with du. Now, I want you to pay attention here, or stop and pause for a second, simply because we are now left with an integral that only has one variable. If at any point in time we are left with two variables, either some x, some y, some u, some v, whatever it may be, if we're ever left with two variables, you're going to stop and you're going to go back to your substitution and you're going to see how you can get everything into one variable. This is very important because we can only do integration with respect to one variable. Now, we can integrate cosine of u du. Well, cosine of u du, we can integrate this quite nicely. The integral for cosine is just sine. Excuse me, the variable that we were doing this with respect to at this time is u. So that's sine of u plus c. However, initially, the integrand was in terms of x. So we have to then make the substitutions to go back to the variable x. So what is the u substitution that we initially made? That was x squared. Which means we get sine of x squared plus c. Notice we got the same answer. So if we can anticipate and if we can know what is the antiderivative, in other words, what function did we take the derivative for to get the integrand, then our job is done. However, if the process is too difficult, then we have to rely on our algebra skills to make a substitution. Then calculus comes in to find the differentials, and then some more substitution comes into play in order to find that integral. So now that we have this process elaborated on, let's go ahead and let's evaluate some integrals. So we're going to evaluate the integral. The first integral that we're going to evaluate is x squared multiplied by sine of x cubed dx. So again, we're only looking for two items here. We're only looking for two of these requirements. So number one requirement, is there a function composition? So I'm just going to write that on screen here, function composition. That's what we're looking for. If we do, let's find it. All right, I see my function composition right in here. Okay, so I see that requirement is met. Great. So what I'm going to do really quickly then is I'm going to extract that. I'm going to say that u is equal to x cubed. Next, we're going to check when I take the derivative of du, does that derivative show up in my integrand? So I'm going to say differential or derivative I'm going to say derivative multiplication in integrand. Okay, so let's try to find that. So in order to verify this, we're going to go through and we're going to take the differential here for du. So we're going to say du is equal to 3x squared dx. So do we see this 3x squared dx in the integrand here? Well, I do see the dx, so that's good. I see an x squared on the integrand. I see an x squared here on my differential, so everything's good so far. However, there is a constant of 3. Now, if there is a constant of 3, that's fine, and that's actually perfect. All right, so don't fret about that. What we're going to do here is we're going to reanalyze this, or we're going to simplify this just a little bit. I'm going to divide my du, or I'm going to divide my differential by 3 on both sides, which then gives me x squared dx. X squared dx, we definitely see that in the integrand. That is awesome. So that is good. Now, I'm going to say here that my x squared dx, that's this piece here. So, oh, sorry, not that piece. My apologies. That's this piece right here. That's 1/3 du. So in order to rewrite this integral, I'm going to go through and I'm going to say the integral for x squared times sine of x cubed dx is equal to my new integral. Remember the function, the substitution that we're going to make, so sine stays the same. So sine stays the same. X cubed is no longer x cubed. X cubed is now u. So I'm making my substitution for u. There we are. You know what? I'm just going to keep everything, and I'll color code in a bit. So sine of u, and then x squared dx, what we have left over in the integrand is just 1/3 du. So that's going to be multiplied by 1/3 du. Remember that 1/3 du, that was my x squared dx. And the initial substitution was there. Therefore, we have an integral with only one variable, and that variable is u. Now, let's simplify this just a little bit more. 1/3 is a constant that's being multiplied, so I am going to factor that out of the integral. Now we have 1/3 times the integral of sine of u du. And all we have to do is integrate. The integral for sine of u, that's going to be negative cosine of u, and we're going to have a constant. Okay, but again, the initial integral was in terms of x. We're going to go back and resubstitute to make sure that our answer is in terms of the variable that was given. So our answer, that's negative, so it's going to be negative 1/3 multiplied by cosine of u was x cubed plus c. And there's our final answer. This is what we want to see. Right? At least this is what I want to see. That's great. Perfect. Now we can double check this. If we take the derivative of this function here, we should wind up with x squared sine of x cubed. So really quickly, let's go ahead and let's run a quick check. Okay, I'm going to do this on the right hand side. So check. I'm going to take the derivative for the answer that I found, negative 1/3 cosine of x cubed plus c. The nice part about the plus c is that when we take the derivative of that constant, it's going to go away. So all we really need to know is what's the derivative of negative 1/3 cosine of x cubed? Well, we need a chain rule for this. Negative 1/3 cosine of x cubed, we're going to take the derivative for cosine of x cubed, so the derivative of the outer function. The derivative of cosine is negative sine. So we have negative 1/3, and that's going to be multiplied by negative sine of x cubed. And then we multiply by the derivative of the inside function. The derivative of the inside function is going to be 3x squared. So we have negative times a negative, that's positive. So we have 1/3 multiplied by sine of x cubed multiplied by 3x squared. Notice the 3's will simplify, they're going to cancel, and we're going to be left with x squared multiplied by sine of x cubed. And that is your integrand. So again, there is a way to check, and the way to check to see if you got the right integral or that you calculated the integral correctly is to take the derivative of your answer. If the derivative matches your integrand, you got it. So that is really good to see. Again, it gives you a method, or it gives you a way to check your work to make sure that you're on the right track as you're doing these problems. Let's investigate another one. The integral for sine of t multiplied by the square root of 1 plus cosine of t, and this is going to be dt. Okay, so again, we want to go through some of these substitutions. And we want to identify those two components. Number one, do we have a function composition? All right, that's one thing that we always want to check. So is there a function composition? Number two, is there a derivative multiplication in the integrand? So function composition, for myself, I definitely see a function composition taking place here. The function composition that I see here, well, first off, I have sine of t multiplied by the square root function. So initially, I do see a multiplication, so that's promising for this second part. Function composition, then, I see that inside of this radicand, I do have a function. That function is 1 plus cosine of t. And that's where I want to begin. I want to say, let me take this whole integrand, let me take this whole radicand And taking this whole radicand, I'm going to make this substitution where I'm going to have 1 plus cosine of t being equal to u. So is there a function composition? Yes. Number 2, I need to find the differential, or the derivative for u. The derivative for u is 1 plus cosine t. Sorry, u is 1 plus cosine t. The derivative is negative sine of t dt. Now, this derivative must be multiplying my function that was being composed in the integrand. There's a slight issue, is that my differential shows me that I have negative sine t dt, but my integrand tells me that I have positive. Again, no need to worry. As long as it's a constant, we are perfectly fine. We can multiply both sides of that differential by a negative, and therefore we get sine of t dt. So is that differential then multiplying the rest of my integrand? The answer is yes. So both of these conditions are met, which means we can go through and keep going with the substitution. So again, my substitution here, I was saying that 1 plus cosine t, that's my u. What's left over, make this 1 plus cosine t, what's left over is this sine t dt. So now, what I'm going to do here is I'm going to go ahead and rewrite this integral, and that way I can go through and start making my substitutions. The integral for sine t multiplied by the square root of 1 plus cosine of t dt is equal to the integral. Now remember, the square root function we're not touching at all. The square root is that main function that we're working with. So the square root function stays as is. So I take the square root, but this time it's not going to be 1 plus cosine t because that's the substitution that I'm making. This time it's u. Okay, so far I got the square root function taken care of. Sine t dt, that's negative du. And so what was happening here is that I took this sine t dt, and that became your negative du. And initially we were looking at the substitution of 1 plus cosine t, that became u. Again, our integral here is the integral with only one variable. We can simplify this. This will be negative, that got factored out, negative integral square root of u. I am going to rewrite this as u to the power of 1/2 du. Therefore, when I evaluate this integral, I add 1 to the exponent, and then I multiply by the reciprocal. Make that negative because of the negative out in the front, and then we have a plus c because this is an indefinite integral. But once again, we have to make sure that our answer is in terms of the variable that was given. So I'm going to resubstitute what was initially u. U is initially 1 plus cosine t. And that's raised to the power of 3/2 plus c. There we are. That's our final answer. Now, I am going to caution you, and I am going to tell you that please be very, very mindful. There are a lot of steps that we need to account for. The steps that often get, let's say, pushed aside or forgotten is to make the resubstitution for the variable that you initially substituted. In other words, some students sometimes leave the answer as negative 2/3 u to the power of 3/2 plus c when the initial variable was t. A lot of other times, students leave out the constant when it's an indefinite integral. So try to make sure you keep track of those steps as you're working through these. That way you can make sure that you maximize the points that you get. Awesome. Let's keep going. Let's try part C. For part C, we want the integral of sine of the square root of x divided by the square root of x, and this is going to be dx. So again, we want to make sure we find those two requirements. Is there a function composition? And then is the differential then that we find for that function composition multiplying inside of my integrand? So I see a function composition. The function composition that I see here is that I have a square root of x. So that's one of the first identifications that I'm making. All right, so let's go ahead and let's write this out. I'm going to have here that u is equal to the square root of x. And since we're going to take the derivative of this, I'm going to write it in exponential form. So that's x to the power of 1/2. I'm going to take the derivative, drop the exponent forward, then subtract 1 from the exponent, and this is dx. Now, it might be hard to see if this differential is in my integrand here. All right, not initially with my substitution, but as part of the multiplication that's taking place. So what I'm going to do here is I'm going to get rid of this negative exponent by using my algebraic tools. And then I don't see a 1/2 in the integrand, so 1/2 is a constant and we can multiply both sides of that differential. So that's not an issue. So multiplying by 2, I get 2 du, x to the power of 1/2 becomes 1 divided by square root of x dx. And so is this portion inside of this differential? The answer is yes. All right, so again, I'm just going to rewrite this. All right, so here we are, sine of the square root of x multiplied by 1 divided by square root of x, again, dx. And so the reason I'm separating this is so that we can see that when we take this differential, or when we take this integrand, we can again decompose it in order to find where our differential is located. So here we do see that I made the substitution. That was my x squared. Sorry, that was my x to the power of 1/2. And we can definitely see that we do have this differential here, 1 over the square root of x dx. Which then means that when I rewrite my integral, I'm going to have the integral of sine square root of x is u, 1 over square root of x dx, 1 over square root of x dx is 2 du. There we are. Again, a function in one variable, or the integral in one variable. Therefore, we can integrate. Let's use some integration properties here. The 2 is a constant. It factors out. the integral for sine of u is going to be negative cosine of u. We're going to have a plus c. And again, let's get the variable in terms of the initial variable that we were given. So this is negative 2 times cosine, and then u was the square root of x. And then we have plus c. And there we are. This is our final answer. And again, you can always double check this. You can double check this by taking the derivative. So let's check really quick. Let's take the derivative for the answer that we found. Negative 2 cosine of the square root of x plus c. Taking the derivative, this will be negative 2, negative 2 times negative sine of the square root of x multiplied by the derivative of the square root of x. Negative times a negative is going to be a positive, therefore we get 2 sine of the square root of x. The derivative of the square root of x, that one is 1/2 multiplied by x to the power of negative 1/2. Notice the 1/2 times the 2 is going to cancel. X to the power of negative 1/2, since it has a negative exponent, it's going to go in the denominator, and therefore we're going to be left with sine of the square root of x divided by the square root of x. And that is the exact same function that is in that integrand. Awesome. So again, we do have these ways, or we do have these methods to check. Now, the methods to check, they are going to be completely a tool. They're going to be a tool that you can use to just check your answers as you're working through. So let's try another one. Let's try the integral for secant squared of 2 theta d theta. So again, what I want to check here is, can I make a substitution? Meaning, is there a function composition taking place? And I do see something here that I have u is equal to 2 theta. And if I take the differential du, I will get 2 d theta. Now again, I have the 2, but the 2 is a constant in this differential, which means I can multiply on both sides, or divide on both sides, which means I just have d theta left over. And that's perfect because I do see a secant squared, and if I make my substitution as just secant squared of u, then my d theta automatically becomes 1/2 du. Now again, my substitution here was that initial substitution. 1/2 du was this, excuse me, was this 1/2 du, that was my d theta. So I'm going to keep going with my integration properties, factor out the 1/2, then that's secant squared of u du. And this is where we want to be, specifically because we know the function that, or we should know the function that we need to take the derivative for in order to get secant squared. So think back to trigonometric differentiation and think back to what function what derivative of a function gets us secant squared? If you answer tangent, then that's perfect. The derivative of tangent is secant squared. Therefore, the antiderivative for secant squared is tangent. This is an indefinite integral, so we must include plus c. Again, the variable initially was not u, the variable was theta. So we resubstitute. 1/2 multiplied by tangent of u, which is 2 theta, plus c. And this is our final answer. Great. Now, let's also talk about the substitution rule when we're using limits of integration. In other words, let's talk about this u substitution or the substitution rule when we have definite integrals. So we're going to go through here and we're going to evaluate the integral. Part A. So for part A, we're going to go from 0 to the square root of pi. So 0 up to the square root of pi. And this is going to be for the function of x times cosine of x squared dx. All right, so let's see how we're going to go about this. Again, we're trying to see if the two requirements are met. First requirement is going to be that we have a function composition. Second requirement is that the differential for the substitution must appear in that integrand using multiplication. So I do see a substitution that I can make here. The substitution that I want to make here, because I see a function composition, is x squared. Once I have this, I'm going to look at the differential du, which is 2x dx. And I do see x dx, but there's a constant here. And again, constants are fine because we can multiply or divide by the constants. So I get 1/2 du is equal to x dx. Perfect. So when I rewrite my integral then, I'm going to have this integral for cosine x squared is now u, x dx, that is now 1/2 du. So again, that 1/2 du, that was my x dx. And then my u was that u substitution that we made here. Perfect. Now, notice I didn't write my limits of integration. And I'm not writing my limits of integration at this time because we need to identify what they are. Since we changed variables, we must change the limits of integration that we have to work with. And one of the things that I'm going to do here is that I'm going to identify on my limits of integration, if my variable is with respect to dx, then naturally my limits of integration are in terms of x. X is bounded between 0 and the square root of pi. But we changed these into u, so now I need to find what are my limits in terms of u. In order to do that, we then need to identify the lower limits going through this substitution. So I'm going to extract that lower limit first. So that lower limit, x is equal to 0. If x is equal to 0, I'm going to use the substitution, u is equal to x squared. And I will be getting here that u is equal to 0. So in the grand scheme of things, my lower limit, x being equal to 0, translates into u being equal to 0. Okay, that's the lower limit. My upper limit, let's try to get a different color here. My upper limit, I have that x, whoa, that's not the color I wanted. There we go. I have that x is equal to the square root of pi. I'm using the substitution for u is equal to x squared. And therefore, I should now get that u is equal to the square root, u is equal to the square root of pi squared. Square root and squared just gets me pi. So my upper limit of integration is just pi. And again, that's in terms of u. So when we're making this substitution, we must always re-index our limits of integration. And this is going to be very imperative as we go through, because we must attach those limits of integration and we must keep the new limits of integration as we change the variables. That way we don't have to go back and resubstitute. So let's finish this off. 1/2 multiplied by the integral from 0 to pi for cosine of u du. The antiderivative for cosine is sine, and that's going to be evaluated from 0 to pi. Evaluate sine at pi minus sine at 0. Again, I don't need the constant because this is a definite integral. So sine at 0, naturally that's 0. Sine at pi, that's also going to be 0. 0 minus 0, 0, which means we get an answer of 0. Wow, very anticlimactic. All right, so that's what we get to see here. Awesome. So this is how we're using the substitution rule for definite integrals. And let's see if we can do one more problem. That way we can make sure we get the fuzzy feeling inside that we know what we're doing. All right, so here goes the next example. We're going to integrate from 0 to 1. And this is going to be for x multiplied by x squared plus 1 quantity cubed dx. So again, we always want to check, is there a substitution that we can make? So here what I'm going to do is I'm going to say yes, there is a substitution, and that is going to be x squared plus 1, because that's my whole binomial on the inside of x cubed. Taking the differential here, du is going to produce 2x dx, and I do see x dx, but I don't see the 2, so I'm going to divide by that. So I get 1/2 du is equal to x dx. Let's make that substitution then. That's going to be the integral. X dx now turns into 1/2 du, and I'm going to have my u cubed multiplied by 1/2 du. Again, the substitution here was taking place. here. Now I need to change my limits of integration. Lower bound, lower limit of integration is x is equal to 0. Let's insert that into my function that I initially made the substitution for. If x is equal to 0, then that means u is equal to 1. Lower limit was x is equal to 0. Now my lower limit is 1. Upper limit of integration, x was equal to 1. I'm going to use the same substitution formula. U is equal to 1 squared plus 1, which gets me 2, which means my upper limit of integration is then 2. Now I can go through and finish off this integral. 1/2 is going to come straight out to the front. Integral from 1 to 2, u cubed du. Let's find that antiderivative. Again, I have my constant of 1/2. The antiderivative, I'm going to add 1 to the exponent, so that's going to be u to the 4th, multiplied by the reciprocal, that's 1/4. And I'm going to evaluate this from 1 to 2. Again, this is a definite integral, so I am not using a constant because, again, it's a definite integral. So let's see, I see a 1/4. I can factor out that 1/4. So it's going to be 1/8. U to the 4th, so that's going to be 2 to the power of 4. Oops. 2 to the power of 4 minus 1 to the power of 4. So 2 to the power of 4, that's going to be 16 minus 1. So our answer is going to be 15/8. And there we are. That's all we need to do. That looks perfect. Awesome. So let's talk about a different type of substitution, one that will require a little bit more work for us to do whenever we're talking about substitution. All right, so let's see that type of integral. So I am going to say here to evaluate, and this is going to be for the integral of x multiplied by the square root of x plus 2 dx. Now initially it doesn't look that bad, and so it's once we start getting into the substitution that we're going to see that it's going to be a little bit different than the previous ones. So I do see a function composition, and I do see a function multiplying that function that is being composed. So what I'm going to do at this time is I'm going to assign u is equal to x plus 2. And so when I look at du, this is just going to give me dx. So again, we're at an issue here that we see u is equal to x dx, and we see du is equal to dx. However, we have x dx that we need to account for. So therein lies an issue. However, there is a way around that issue, and the way around that issue is going to be for us to make a resubstitution for what x is. Because again, our overall goal is to get a new variable, a new integral with only one variable. So let's try that. Take this integral, we now have the square root x plus 2, that's my u. All right, that's great. But now I have my dx. My dx is just my du. Okay, so dx, that's just my du. My initial substitution was the square root of u. Sorry, was u is equal to x plus 2. I need to account for that x. And the way I'm going to account for that x is that I am going to use this substitution here. U is equal to x plus 2. If u is equal to x plus 2, then x, solving for x in this equation, is going to give me that x is u minus 2. Therefore, whatever x is that's multiplying my square root of x plus 2 can now be interpreted in terms of u. So my x variable now turns into u minus 2. There we are. Now we have an integral with only one variable. Integral with only one variable, that's perfect. That's what we want to see. So we have u minus 2 multiplied by the square root of u. And remember, we always want to express the square roots or the roots in terms of exponentials. That way we can integrate them easier. Let's distribute the u to the 1/2. U to the 1/2 times u should get us u to the power of 3/2 minus 2 times u to the power of 1/2 du. We add 1 to the exponent when we integrate. Should get us 5/2 multiplied by the reciprocal. Add 1 to the exponent. 1/2 plus 1 gets us 3/2 multiplied by the reciprocal. Should get us 4/3. This is an indefinite integral, so we add the plus c. However, we're not solving for u at the very beginning. We're solving for x. So we're going to go through and we're going to resubstitute x. Resubstituting in the value of x, we now get 2 divided by 5 times u was x plus 2. So this is x plus 2 to the power of 5/2 minus 4/3 multiplied by x plus 2 to the power of 3/2 plus c. And there's our final answer. So again, we are able to attain this final answer, and it's actually a quite nice final answer. All right, and you can go through and you can double check. Take this derivative and see if you get the integrand that we initially started with. If we can, that's awesome. All right, and I guarantee that we will. Now, let's look at an example where we're going to have to use the same process, almost the same technique. However, we might have to do something slightly different. And let's see what that slightly different technique might be. So here we go. Let's go with evaluate the integral from 1 to 5 for x divided by square root of 2x minus 1 dx. All right, so we can try a few different substitutions here. Now, one of the substitutions that I want to focus on here is going to try to be, or is going to try to find this integrand in order as a good substitution. So there are different substitutions that are taking place here. We could say that u is equal to 2x, or we could say that u is equal to 2x minus 1, Or we could say that u is equal to the square root of 2x minus 1. So there are different substitutions that can take place. Now, it's not to say that one substitution is better than the other, but there might be along the same lines of a substitution that will lead you to the exact same result. So again, there might be multiple paths that you can take to get you to the exact same result. And so that's what we want to investigate. So let's go through and let's try to investigate this. All right. So what I want at this time, just to see what happens here, is that u is going to be equal to the square root of 2x minus 1. Now I know what you might be saying. Well, if that is the u substitution, then when we take the derivative, we're going to take the derivative of the square root of 2x minus 1, which will slightly be more complicated, and it won't give us the differential that we need. And I will say that you are correct. So this is the initial substitution where if we anticipate what we want, we don't get exactly what we need. However, there is a way around this. What if instead of taking the derivative automatically, I don't take the derivative? What if I square both sides? Okay, well that's interesting. So squaring both sides, okay, not bad, but where am I going with this? Well, look at your numerator. Your numerator has an x. If we're making this substitution, can we solve for x? In other words, can we find what x is? Well, let's go ahead and try. We don't know until we try, which means x is just 1/2 multiplied by u squared plus 1. Interesting. Now what happens if I take the differential here? I still get a dx. Differential here, dx. Okay, that's awesome. Differential on the left-hand side. Well, on the left-hand side, I'm only taking the derivative of u squared, but that's going to be multiplied by 1/2, so I should get just u du. Nice. So I do have a differential that I can extract, and I do have some substitutions that took place. Let's look at those substitutions. All right, I'm going to decompose all of this, my integrand here, so I'm just going to rewrite this. I have x multiplied by 1 divided by the square root of 2x minus 1, and that's still dx. So my substitution here, x, is the variable that I'm looking at here. So that x is my 1/2 times u squared plus 1. Okay, that was the x. And I'll highlight all of this in just a bit. I have multiplying by 1 over the square root of 2x minus 1, but the square root of 2x minus 1, that was my initial substitution for u. My dx is u du. So let's go through and let's pause really quick and let's analyze where everything came from. So my analysis here is that x was this value that I manipulated, this 1/2 times u squared plus 1. My initial substitution is the square root of 2x minus 1, and that was my u. My differential then comes in the form of u du is equal to dx, so I know what dx is, and that was my u du. Now there is something missing here, my lower bounds and my upper bound. So my lower bound says that x is equal to 1, and if x is equal to 1, then I need to find out what my u variable is, because my new integral is in terms of u. So initially we have that u is equal to the square root of 2x minus 1. So let's make the substitution of 1 into that x value. 2 times 1 minus 1 should just get us 1, so the square root of 1 is just 1. Lower bound of x is equal to 1 now translates into x is equal to 1. Awesome. Upper bound. Upper bound, I have that x is equal to 5. Again, I'm using u is equal to the square root of 2x minus 1. Therefore, when I make the substitution, 2 times 5, that's going to get me 10, minus 1, that gets me 9, square root of 9 gets me 3. Therefore, my upper bound, when x is 5, u for the upper bound is going to be 3. Let's see what we can do now. I have a constant of a half, so that comes straight out. Integral from 1 to 3. I see a u in the denominator, but I also see a u in that numerator, which means they will simplify. And I should only be needing to integrate u squared plus 1 du. Let's integrate this. The integral for u to the power of 2, I'm going to add 1 to the exponent, multiply by the reciprocal. Integral of 1 with respect to u, that's just going to be u. Evaluate this from 1 to 3. So this is 1/3 times 3 to the power of 3 plus 3 minus 1/3 times 1 to the power of 3 minus 1. All right, let's keep going. 3 cubed, that's 27, divided by 3, that's 9. So that's going to be 9 plus 3, that's going to be 12. And then here I'm going to have 1/3 minus 1. So 1/3 minus, negative 1/3 minus 1, that should get me 4/3. And so now I'm going to do 12 minus 4/3. So I'm going to multiply the 12 by 3. That's going to get me 36. I'm going to subtract 4, and that should get me 32. So this is 1/2 multiplied by 32 over 3. And 32 is divisible by 2. It should get me 16. So my final answer is 16/3. And there we are. There is our final answer. So when we're making this substitution and when we're looking at the differential, there might be an instance where we then have to manipulate that substitution in order for us to be able to fully evaluate this integral. So I thank you all for joining me for this lesson, and I hope you enjoyed it, and stick around and we will be coming back on to chapter 5. Till next time, I'll see you then.